Welcome to this session. This session, we are going to discuss about linear dependence and linear independence. So let's start by definition. Definition of linear dependence. So we say a set or a set of vectors S given by V1, V2, V3 up to Vk in a vector space V is said to be linearly dependent if the vector equation C1 V1 plus C2 V2 plus C3 V3 up to plus CK Vk equals to 0 for some scalars C1, C2, C3 up to CK. These are real numbers where at least one of the CIs C1, C2, C3 up to CK is non-zero. The definition of the set of vectors V1, V2, V3, Vk in a vector space V is said to be linearly dependent. So this is the key term, linearly dependent, if the vector equation C1 V1 plus C2 V2 plus C3 V3 up to plus CK Vk equals to a zero vector for some scalars C1, C2, C3 up to CK, where at least one of these real numbers C1, C2 up to CK is non-zero. So that's what we call linear dependent set. And then if this set of vectors V1, V2, V3 up to Vk is this set of vectors is linearly dependent, then it is possible to write any vector, any of these vectors as a linear combination of the remaining vectors. That's, that's what we need to note. And then let's give the definition of linear independence, and then we'll do some examples. So definition, linear independence. So a set of vectors as vectors v1, v2, v3 up to vk in a vector space V is called linearly independent if the vector equation C1 V1 plus C2 V2 plus C3 V3 up to plus CK VK equals to 0 has only the trivial solution, i.e. C1 equals to C2 equals to C3 equals to CK, and all these scalars are 0. And then, so the key thing here is that to define linear dependence and independence, we have to have this vector equation. And when you solve this vector equation and you get all the scalars C1, C2 up to CK, all of them are 0, then you say that set of vectors V1 to VK is linearly independent. But when you find that at least one of the Ci values is non-zero, then you conclude that the set is linearly dependent. And then if S, this set of vectors V1, V2, V3 up to VK is linearly independent, then it is not possible to express or write any of these vectors as a linear combination of the remaining vectors. Vectors. So that's what we mean by linear independence and linear dependence, and what they imply, that for the case when vectors are linearly dependent, then you can write one vector in terms of other vectors or as a linear combination of the other vectors. But a case whereby vectors are linearly independent, then it is not possible to write those vectors, any of the vectors as a linear combination of the remaining vectors. So examples. So we say the set, this first example, the set S1 given by these two vectors, 1, 2, and then 2, 4 in R2 is linearly dependent. So quick proof. So if we let this one to be V1, let this one to be V2, then you say S1 is linearly dependent if and only if the vector equation C1 V1 plus C2 V2 equals to 0 vector has at least one of C1 or C2 non-zero. So let's have C1, V1 is 1, 2, plus C2, V2 is 2, 4, and a 0 vector in R2 is the same as 0, 0. So this will be C1, comma 2C1 plus C2, 2C2, comma 4C2 equals to 0, 0. And for this equality to make sense, so let's get the sum on the left. So C1 plus 2C2, 2C1 plus 4C2 equals to 0, 0. And then for this equation to make sense, then C1 plus 2C2 should be 0, and 2C1 plus 4C2 should be 0. Now, if I call this equation 1, this equation 2, we have from 1. Now, this is just a system of two linear equations in two unknowns, C1 and C2. So from 1, C1 equals to minus 2C2. So replacing, if I call this one 3, replace 3 in 2, i.e., while the C1, I put minus 2C2 plus 4C2 equals to 0. So this will be minus 4C2 plus 4C2 equals to 0. And you see 0 equals to 0. So this makes sense. So which means that then C2 is free. So this implies C2 is free. And so we let C2 to be, say, T, which is a real number, so that we can say C1 is given by minus 2T. So the solution set for this system is C1 is minus 2T and C2 is T. So this is a solution set. So when we let T to be, say, 1, then C1 will be minus 2 and C2 will be 1. So that we'll have minus 2 V1 plus V2 giving us a 0 vector. So we can write minus 2. V1 was 1, 2, and then plus 1 into V2 is 2, 4. This is 0, 0. So therefore, V1 and V2 given in S1 are linearly dependent, because at least you see we have both C1 and C2 are non-zero. So this is 1 and then 2. Example 2, the set S2 given by vectors 1, 0, 0, 1, and -2, 5 in R2 is linearly dependent since now you can show that twice 1, 0 plus -5, 0, 1 plus 1 -2, 5 is given by 0, 0. You see, this would be 2, 0 plus 0 minus 5 plus -2, 5. And this will be 2 plus 0 plus -2, 0 plus -5 plus 5. And indeed, you see this 0, 0. So therefore, this set is linearly dependent because these CIs, all of them are non-zero. Number 3, the set S3 given by the vectors 0, 0, then 1, 2 in R2 is linearly dependent since we can say 1 times 0, 0 plus 0 times 1, 2 gives us the 0 vector. And then number 4, the set S4 given by just this single vector is linearly independent subset of R. Number 5, the set S5 given by these two vectors 1, 0 and 0, 1 is a linearly independent subset of R2. That means that C1 V1 plus C2 V2 equals to 0 vector will only be true when C1 and C2 are 0. Number 6, the set S6 given by these three vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 is a linearly independent subset of R3. That means that C1 V1 plus C2 V2 plus C3 V3 equals to 0 vector is true if and only if C1 equals to C2 equals to C3 equals to 0. And then number 7, the set S7 given by just this single element 1 is a linearly independent subset of the set of all polynomials of degree 0. Number H, the set SH given by 1 and X is a linearly independent subset of P1. P1 means the set of all polynomials of degree less than or equals to 1. Number 9, the set S9, which has 1, X, and X squared, is a linearly independent subset of P2 with a set of all polynomials of degree less than or equals to 2. And lastly, number 10, the set S10 given by 1, X, X squared, and X power 3 is a linearly independent subset of P3. P3 means set of all polynomials of degree less than or equals to 3. So the next session will be giving examples on how to determine when you're given an arbitrary set, whether it is linearly dependent or linearly independent. Thank you.